So let's take a step back for a moment and look at the bigger picture. Maybe not the big picture, but certainly a bigger picture than all of these little tiny boxes that we've been looking at for a while. So we started our thinking about boxes a long time ago because we're interested in fractals. Fractals are objects that show self-similarity across many different scales. We see the same sort of pattern repeating at large scales, smaller scales, smaller scales, and smaller scales still. And the signature of that is what we're seeing on these log-log plots. What we see when we do box counting is, say for a two-dimensional object, every time we half the size of the boxes, the number of boxes we need goes up by 4. We half those boxes, we need 4 times as many. We half those boxes, we need 4 times as many. So that's a mathematical relationship, just a pretty simple counting relationship, but it's constant across scales. Just like every time we zoom in on the Sierpinski triangle, we see 3 smaller triangles. We zoom in again, we see 3 smaller triangles. We zoom in by a factor of 2, we see 3 smaller triangles, and so on and so on. So a straight line on a log-log graph shows us that there's something multiplicatively constant occurring across those scales. And multiplicatively constant, what I mean by that is, well, just what I was saying earlier, that say every time we zoom in by 2, we see 3 times as many things. Every time we zoom in by 2, we see 3 times as many things. Every time we half the box size, we need 4 times as many boxes, or whatever it is. So log-log plots are, again, the signature of fractal behavior. We call this scaling. And as the course progresses, we're going to be focusing more and more on equations like the box counting dimension equation and log-log behavior. And we can see, what we'll see is that it's not just spatial fractals like snowflakes and diffusion limited aggregation that have these, this type of behavior, but many other systems do as well. All right, so let me say a little bit more about dimensions and log-log behavior and what they're telling us before we conclude with this unit. So the idea behind dimensions applied to fractals is looking at how the properties of an object change when we change the scale at which we view it or analyze it. And in particular, a dimension, when we can define a dimension, that says that actually there's something that's staying the same even when we change the scale of the object, the scale of our analysis. So, for example, the Sierpinski triangle that consists of these 3 triangles, and here's a triangle, and that's those 3 triangles, and this triangle is half the size of the big triangle. Here's a triangle, here's a small triangle that's half the size of this triangle, which is in turn half the size of that triangle, and every time we look at another triangle, we see that it's made up of 3 triangles. So that halving of size, tripling of triangles, that's a relationship that stays the same across scales. That's how we started thinking about dimensions, with this idea of the self-similarity dimension. Number of small copies equals magnification factor to the d. And we said in order for something to be a fractal, this has to hold across many different scales, so that you can take this, magnify it by 2, take this, magnify it by 2, take this, magnify it by 2, and so on. So then, in this unit, we've been looking at box counting. And the box counting dimension is given by this relationship. NS is C 1 over S to the D. And we can take logs and come up with this. And again, these 2 equations are exactly the same. They've just been manipulated. This has had its log taken and simplified a little bit. So we can make a plot, and we did this some. of log s first log n, and if there's something that stays the same when the scale is changed, then this is going to show up as a line, and we would have a constant slope d. It's worth reminding ourselves that not everything is a fractal. We could do box counting and get something that's not linear, and that would mean that it's not a fractal. No big deal, nothing wrong with not being a fractal. Again, not every shape is a fractal. There are even really interesting, cool shapes that aren't fractals. But if something is a fractal, we can define the dimension this way, and it's telling us that something is staying the same when the scale is changed. Now, there are a number of other different notions of dimension, but they're all, at least in the context of fractals, they're all based on this same idea, looking at how the properties of an object change when the scale of the object or the scale of our analysis changes.